All right. Let's knock off a little bit of chapter 3, and this way we can have more time to do other things later. All right. So we talked about probabilities. We talked about data. I think it's time we put those two together, and for that, we're going to be looking at probability, but not probabilities in the sense of chapter 1. We're going to be rather looking at probabilities for discrete sets, so discrete probabilities. Right. Well, we're going to start with some vocabulary. Random variable is one of those terms we're going to be using a lot, and a random variable, some x, right, is random variable x that has a value for each outcome of a procedure, right? And again, since we're talking about probabilities, we need determined by chance. So if we have a procedure and it produces some outcomes, each one of those outcomes should have a value attached to it. That's a random variable. And then a probability distribution, just like frequency distribution, is just a table, a chart that gives probability for each value of a random variable. And again, we're talking about usually a table, but charts work for it as well. So an example of a probability distribution looks the following. If we consider this to be a coin and we assign 0 for heads, 1 for tails, this is a probability distribution for a coin flip. A 50% chance of getting heads, 50% chance of getting tails, and the coin doesn't have any other outcomes. It has heads or tails. We ignore, in mathematics, coins don't have an edge, so they cannot stand on an edge. I know, I saw the YouTube video too. We're looking at this, which means that we could also look at to specify random variables into discrete random variable, and this is a variable with a finite, which means countable. If you remember chapter 2, finite or countable number of values. We could have a continuous random variable which would have infinite number of possible values. Say heights are infinite, age if you're a small kid, or you can have something that is finite and countable. Number of people in the room, for example. You walk into different classrooms and take a look at how many people are in the room. There's a finite number of people you can have in a room. So that's that. All right. We could do histograms. For probability distributions, and that's again very pleasant, although doing a histogram for a coin is a little sad. So how about we take a look at a weighted die? I mean, we talking statistics, might as well have some fun with it. So a die would have 6 sides, right? So we have 6 values for all the outcomes, right? 6-sided dice has only 6 outcomes because you can land on one of the sides, and we can assign some probabilities to it. Right? Well, there's a couple things we need to make sure. First of all, probability, as we know from chapter 1, has to be that. So each one of those has to be a positive number between 0 and 1. Can it be 0? Sure. Can it be 1? Sure. But if one of those is 1, the rest of them have to be 0. So those are extreme cases. Can it be 0? Sure. We could have a die that doesn't have one side. 6-sided die where one side just won't end up being rolled ever. It's weird, but second of all, sum of all the probabilities has to be equal to 1. And why does it have to be equal to 1? It has to be equal to 1 because those are all the outcomes, right? Right? Each outcome, so this is all the outcomes, there is nothing else. So sum of all of this have to be 1. Now, in some cases, the sum of this can be slightly smaller than 1 or slightly larger than 1. The reason for it is because usually those probabilities are observed probabilities, which means that we are doing some math. If we do some rounding, those numbers might not completely add up to 1, and that's okay, but that difference from 1 has to be very, if not extremely small. So just a heads up. And then we can do a histogram. 1, 2, 3, 4, 5, 6, 5%, 10%, 15, 20, 25, 30, 35. So let's see. First one is 1. That's 5%, so let's call it 0.05, 0.10, 0.20, 0.30. So this is the first one. Second one was 15, so that's this. 35, that's that. Then it's 30, that's here. Then it's 10, and then it's 5. And here's your histogram. 1, 2, 3, 4, 5, and 6. Easy. Alright. What else can we do? Well, we could calculate the mean. We knew we could calculate the mean for a frequency distribution, and that was fun to do. Again, why I'm using n? Because we have all the data, right? So there was midpoint times the frequency. In this case, we don't have a midpoint, you just have an outcome, so that just turns into just an x. So the mean is sum of x times, well, what is f divided by n? The frequency of something happening divided by the total number of individuals. So say everybody in your family who wears glasses divided by everybody in your family gives you the probability of finding somebody with glasses. So this little section becomes that. So the mean equals the sum of x times p of x. The value for the outcome times the probability of the outcome occurring. And that's relatively straightforward to do. So let's do a big table and show that. Right, so we have our table with 1, 2, 3, 4, 5, 6. That was our x. Our p of x was 0 0.05, 0 0.15, 0 0.35, 0 0.30, 0 0.10, and 0 0.05. And if we multiply them together, x times p of x, that comes out 0 0.05, 0 0.30, 1.05, 1.2, 1.50, and 0 0.30. And if we sum x times p of x, we get 3.4, which means that the average, the mean, right, is equal to 3.4. It doesn't mean we are expecting to roll a 3.4. It means that if we keep on rolling it forever and ever and ever, the average of all those rolls is going to be approaching 3.4. Right? So that was easy. What else can we do? We could calculate the standard deviation. And again, the variance equals to that. Alright, well, there's a couple ways we can get x squared times p of x. We could multiply this times x, right? X times x is x squared, so we could go x times p of x. That's one way to do it. The other one is we could find an x squared and then multiply x squared times p of x. So there's two ways we can do it. If we do it the first one, we're just going to multiply those two, and we're going to get 0 0.05, 0 0.60, 3.15, 4.80, 2.50, and 1.8. If we do x squares, then we're going to go 1, 4, 9, 16, 25, and 36. And then x squared times p of x is 0 0.05, 0 0.60, sticking everywhere, 3.15, 4.8, right, 16 times 0.3, 2.50, and the last one is x squared, 1.80. Right, so either do this times this gives you that, or we go p of x times x squared gives you this. There's two ways to do it, and either one of them gives you the same solution. And so we sum this up, so sum of x squared times p of x equals to 12.9, right? Which means that our variance equals to 12.9 minus 3.4 squared. So that equals to 12.9 minus 11.56. So that comes out to be 1.34. That's the variance. What's the standard deviation? Well, standard deviation equals to square root of the variance, which means it's equal to square root of 1.34, which comes out to be 1.16. That's variance. This is standard deviation. and that's the mean. For completion, we could probably write this. Which is the square root of this. Again, there's online calculators for this to do. I just expect you to know how to do it rather than to do it over and over again. All right, so that was great. Well, again, so let's talk usual and unusual. Right? What's usual? Well, that's within 2 standard deviations, and this is outside of 2 standard deviations away from the mean. So in our case, our mean was 3.4. Our standard deviation came out to be 1.16. So this is mean plus 2 standard deviations. So that's 3.4 plus 2 of those. That comes out to be 5.72. Right? So it's 3.4 plus 2 times 1.16. And on this side, we have a mean minus 2 standard deviations, which means 1.08, because that's 3.4 minus 2 times 1.16. So that's the usual range. Are any of our scores unusual? Well, let's take a look. We need something that is smaller than 1.08. Well, we have. This is unusual. And we need something that's bigger than 5.7. Well, 5 is smaller, but 6 is bigger. So those are unusual. And here's the trick to it. If I asked you what's unusual, you could do this. Or you could take a look at this. 5%, right? 2 standard deviations away means 95% of the data. So anything that is smaller or equal to 5% is unusual. These two things are unusual. Because unusual also means probability that is smaller equal to 5%. Right? If P of A is smaller or equal to 0.05, which is 5%, A is unusual. Right? Chapter 1 says hello. All right, so this is just a little introduction. Let's keep going. What can we do with this? Well, we could look at this somewhat interesting case of binomial probability distribution. And binomial probability distribution is a probability distribution that has only 2 outcomes. It has success and failure. Now, when we say success and failure, I don't mean real life success and failure, I mean the term success and failure. So if we ever do any questions talking about success and failure, say with probability of having a boy or a girl. I don't mean one of them is a success, the other is failure. The standard disclaimer, this is mathematics. This is how we define things. This is the words we use for it. Alright, so couple rules, and those are important. Again, don't have to memorize it, have to be aware of them and somewhat function in this environment. So the rules are: one, you must have a fixed number of trials. Now, we say fixed number of trials rather than the sample size, but both of those refer to the same type of data, which is how much data you have. And fixed number, which means that we run from A to B and it doesn't expand. So if you drawing cards from a deck, what you're going to do is you're gonna do the little shuffle, and we can split the cards into two outcomes: red being success, black being failure, right? Let's do that. Success and failure. And what I'm going to do is I'm going to pick 5 cards, and what's the probability I'm going to find 3 hearts? Picking 5 cards, what's the probability of getting 3 hearts? So I'm going to start picking 1, 2, 3, 4, 5. Ta-dam! Right? But I'm not allowed to do the following. I'm not allowed to be like, hey, 1, 2, 3, 4. I'm gonna make it 6 cards just in case. No, I'm gonna say because every time you draw more cards and more cards and more cards, you're changing the overall probabilities, because the number of trials are changing, which means that certain probabilities in that set are going to be changing. So when you decide on the number of trials, that it's it. If you decide to change the number of trials, we have to redo the calculations. 2. Trials must, and underline here, be independent. Which means that each trial that you do, right, cannot be affecting another trial. So in case of deck of cards, if I say, hey, I'm going to pick 5 cards, I have to do it with replacement, because drawing a card changes the probabilities of all the following cards. So what I'm going to do is I'm going to give it a shuffle. I'm going to pick a card, black. I'm going to shuffle it back in. Shuffle. Pick a card, red. Shuffle it back in. And so on, red. And so on and so forth. Black, and then the last one, red. Right? So what I did is I had to reshuffle every time. Why? Because my trials need to be independent. Otherwise, this doesn't work. And independent means the outcome of one trial doesn't affect the next one. Third one, each trial has only 2 outcomes. AKA, if I'm drawing a set of cards, I won't be getting a card that doesn't have a color on it, like a blank card, for example. Right? If you're having kids, either having a boy or a girl, no unicorns are allowed. Only 2 outcomes. Why? Well, it's binomial distribution. It's based on 2 outcomes. And 4, which is very much connected to number 2, is the probability of success remains the same in all trials, which means that when I'm picking the cards from the deck. Halfway through the testing or the trials, somebody doesn't go like, oh no, don't use this deck, I want a fresh deck. And you're like, well, but and you're like, no, let's do it this deck. And you're like, well, but this one has the jokers in it. And I'm like, well, right, probabilities change, and you cannot do that. So there's the two main things. One is the trials must be independent. The second one is the success rate has to be the same. All right, so there's a couple things here. So n we define as the number of trials that we're gonna repeat and do. Then we have p, small p, which is the probability of success or successful outcome success in a single trial. We have a small q, which is the probability of failure in a single trial. And of course we should know that p plus q equals 1, because p and q are complements. If you pick a card, it's either red or black. There is no purple, there's no nothing, right? Either have, if I want to pick red cards, you either have a success or you have a failure. You don't have a third option. So p and q are complements, which means that p equals to 1 minus q, q equals to 1 minus p. So we can do a lot of those little things. P equals 1 minus q, q equals 1 minus p, and q equal to 1. So we have this kind of extra thing. Then we have x, which is the number of successes in n trials. And then we have p of x, which is the probability of x successes. All right. So that's the basics. So let's think about it. So if we decide to roll our weighted die, and we know that the probability of rolling a 4 was 30%, right? Remember that table we just did. Then if we roll the die 10 times, what is the probability to roll 8 4s? I want to roll the die. So first things first, rolling a die, the roll of a die are independent. We have a fixed number of trials. Yes, we're going to do it 10 times, right? Each trial must has 2 outcomes. Well, yeah, you either roll a 4 or you don't roll a 4, right? And probability of success remains the same in all trials. Yes, because we have the same die, and dice don't change the more you roll it. So let's take a look. N is the number of trials we're going to run. 10, check. P and Q. If we have P, we can figure out Q. If we have Q, we can figure out P. What is P? Well, for that, we should probably define what we define as success. In this case, I'm going to say rolling a 4 is a success. Well, then what's failure? Well, not rolling a 4. Right? Either you're in or you're out, kind of thing. What does mean not rolling a 4? It means 1, 2, 3, 5, or 6. If you roll any of those, that's a failure. Well, if success is rolling a 4, and rolling a 4 has 30% success rate, well, then 30. Well, what's Q? Well, Q is 1 minus P, so in this case, it's 1 minus 0.3, so it's 0.7. And then our X was what? X was the number of success in n trials. How many successes do we want? Well, we defined rolling a 4 as a success, so we want 8 successes. So what we are looking for is P of X. What we are actually looking for is P of 8. Right? That gives you that. Okay, now let's so what can we do with this? Well, first of all, remember chapter 1? We had something about the combination of things. So if we are looking at probability of 8 successes, we are really wondering how do we do this? Let's do it this way. Yeah, let's do this. What is the 8 successes going to look like? Well, let's consider blue cards referring to rolling a 4, and and there's 8 of them, and then 2 cards of not rolling a 4, which are the black ones. Can you tell the difference? It doesn't look too good. Hang on, let me just grab some. Again, I got a couple comments saying that the visuals are nice, so I'm trying to work with the visuals. If you guys prefer cards over stones, just let me know. I'll readjust. But okay, 1, 2, 3, 4, 5, 6, 7, 8, and then 2. So if we are planning on rolling 8 4s, right, there's 8 of those stones and 2 of those. If I'm planning on rolling 8 4s, 8 of the, the white stone represents 4s, and then this one they represent the not 4, success failure. If I'm planning on doing this, how many ways can I do it? Well, I could just be lucky and roll all the 4s in a row and then roll the 2 failures, right? Or I could roll the 2 failures at the beginning and then roll all my 4s, right? Or I could roll a 4, a non-4 here, non-4 here, and then right, and so on and so forth. Can you tell a difference between this setup and this setup, or this setup and this setup? Well, no, because those are either 4s or non-4s, and I don't care if this was a 1 and this was a 6, or this was a 6 and then this was a 1. So what I'm looking for is all those possible arrangements that will satisfy this condition. So out of all of those, I'm going to have to pick 8. Right? Why combination? Again, because if I do this, you won't know the difference. If I take all of those and then just move them around, right, I still have the same thing. So we're looking at combinations. Then we are going to have to roll the 4s. How many of them? 8. So we have to roll 8 of those, right? Probability of a 4, and then a 4, and then a 4, and then a 4, and then repeat that 8 times. Are we done? Well, no, because after we roll 8 4s, we still have to roll 2 more times, and those 2 more times we have to fail, right? Because if I asked you to draw if I ask you to draw 10 cards and 8 of them has to be black, okay, 1 2 3 4 5 6 7 8. I asked you to draw 10 cards and 8 black. So you draw me 8 black cards and you're like, I'm done. I'm like, no, I asked you to draw 10 cards. Also, you have to draw, you have to draw a red and then a red. Because otherwise it doesn't make sense. I asked you for 10 cards. 8 of them have to be 4s. 2 of them have to be something else. Alright. So this is it. So this is our equation. Well, then let's solve it. So P of 8 equals to, what's 10 C8? Well, we can do it on a calculator, and that comes out to be 45. So this becomes that. Then 0.3 ends up being 6.561 times 10 to the negative fifth. For people that are wondering, 6.561 times 10 to the negative fifth, what the hell is that? If you do this calculation, 0.3 to the 8th power, what you will get out of this is you're going to get something that looks like this. You're going to get that on your calculator. We can, if we write this, we can write this as what? As we could write this as 6.561 divided by, well, how far we have to do it? Times 10 times 100 times 1000 times 10,000 times 100,000. Right? These two things are still equal. Well, what is this? Well, this is 6.561 divided by 10 to the fifth. And if we're dividing by 10 to the fifth, it's equal to us 6 times 10 to the negative fifth. That negative means we divide by 10 to the fifth power. Right? So this notation is this. On your calculator, you can also get something that looks like this. E10. That also means you multiply it times 10 to 10 E5, or 10 to the fifth, or negative fifth, or there's some notation in this. Let's see what the TI does. 0.3 to 8th power. TI-30 has both scientific or float. If you're doing float, which is the button up here, the blue one, second this, you have 3 options. Long, scientific, which is, right, this is the negative fifth. So either get e to negative 5, you get 10 to the negative fifth. You have some notation here, and that's this number. And then you have this, which is times 0.49. Three of those 3 things. All right. do not round those numbers, because if you do, it will affect the rest of your calculation. And then this is 8, so this ends up being 0.00144467. So that P of 8 equals 2. Well, I wanted to in percentage, so times 100%, it will end up being 0.145%. So the probability that even on my weighted die, you're gonna roll 8 out of the 10 times you're gonna roll a 4 is only 0.145%. Oh my god. Nah, doable. Again, there are ways to calculate it using other methods, but this one is relatively straightforward. Alright, so now let's figure out what the actual equation that we're going to use is going to look like. So binomial probability formula. Alright, so that's P of x equals to what? Well, this is the number of trials we had, combination x out of n, right, times probability of success to the power of x, right, how many successes we had, times failure, right, to the power of what? Well, what's 2? Well, 2 is n minus x, and that's the formula. And this is how you do it. Just plug and play, and your calculator can do most of it for you. Alright, so now let's see if we can get this. Right, super. Right, super. So if you have your tables, pull up your tables, and let's keep on going. So what happens if I want a probability of rolling at most 8 fours? Well, at most 8 fours means what? Well, it means probability of 0. 0 fours is at most 4, right? Probability of 1, probability of 2, plus probability of 3, plus probability of 4, plus probability of 5, plus probability of 6, plus probability of 7, plus probability of 8. Oh wow. Addition rule, right? Disjoint sets, no crossover, right? This is going to be probability of 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. Wow. Well, again, there's calculators online that can do it, but let's do it by hand so we get a feel for it. Well, we know what probability of 8 is. We just calculated this. Do you really want to do this for all the other ones? I didn't think so. I don't either. I really don't want to do it either. So we're going to reach for a either an online calculator or a table. If we reach for a table, we're gonna, oops, sorry, wrong button, this one. We're gonna reach for the table, we're gonna get this. So what we have here is we have an n, a column for n, we have a column for x, and we have a column for p. N is the number of trials, x is the number of successes, p is the probability of success in a single trial. So our n is 10, right? We had, where's the setup? Our n was 10. So, right, our n was 10 and our p was 30%. So we have to scroll down to 10, which should be right here. And then we're looking for our axis. Well, our axis is 0, 1, 2, 3, 4, 5. Okay, what's our p? P turned out to be 30%. Right, this is what we have from the question. So what we're looking for p at 30%. So we're looking at this column right here. And then we're looking for what? Well, we're looking for p of 0, right? We're looking at p of 0. Actually, maybe I should do the following. We're looking at p of 0. So right here. Right, so our p of 0 is that. And then p of 1, p of 2, p of 3, p of 4. So we pretty much have to add all of the column from starting from 0 ending at 8. So we have to add p of 0 plus probability of 1, 2, 3, 4, 5, 6, 7, and 8. And if you all add all of those up, 0.028 plus 0.121 plus 0.233 plus 0.267 plus 0.2 plus 0.103 plus 0.037 plus 0.009 plus 0.001, we get an answer that looks like this. So this whole thing is 0.999. Okay, that was easy. So there's a couple things we need to understand. First of all, if you look at probability of 8, according to the table we just saw, that's 0.001. We know that it's not. It's 0.001447. Why is there the difference? Because the table is rounded. And because the table is rounded, all those probabilities not necessarily will add up to 1. They will be about 1 after you add all of them up. So that's 1. Second of all, that 0, 0, 0 that you saw right here, that doesn't mean 0. That just means that the probability of rolling 10 fours out of 10 rolls is about 0, 0, 0 because it's rounded. So there's just this little thing. So don't write this is equal to 0, say about 0. Just like if you add p of 0 plus p of 1 plus ta 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 plus p of 9 plus p of 10, this should equal to 1, even though if you add all of them up, there will be 0.9999 because it's rounded, right? same way, if p of 0 plus p of 1 plus p of 9, missing the p of 10, that doesn't equal to 1. Even though p of 10 is 0, this is about 1. This is not equal to 1. Equal has a very strong and powerful meaning, so we have to be extremely careful when we use 1 versus when we say about 1. Same with this. Probability equal to 0 has a very specific meaning. Probability about 0 tells us that for all the foreseeable digits, it's about 0. It's very, 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 very unlikely, but it's not impossible. Right? So there's this thing. All right. So that should help with that. Again, let's take a look. Nope, still crazy, still talking to myself. All right, so that's the binomial formulas. All right, let's keep going. All right, how about mean and standard deviation, variance while we at it, of binomial probability distribution. Well, the mean is the expected number of successes, and the mean is calculated n times p. So in our example where p was 30% and n was equal to 10, what did we expect? Well, we expected the mean to be 10 times 0.3, which is equal to 3, which means that we are expecting in 10 dice rolls to roll 4 3 times. Right? That's what the mean means. Then variance was sigma squared n times p times q. Well, in our case, variance would be 10 times 0.3 times, well, what was q? Q is 1 minus p, so that was 0.7. For that, I'm going to be cheating. And that came out to 2.1. So that's our variance. And then 3, our standard deviation, equals square root of variance of npq square root. And that came out to be 1.45. That's the difficulty of calculating the mean standard deviation of a binomial probability distribution. Okay, what else can we do? Well, we could ask for the usual what's the usual number of 4s you would roll? Well, how many rolls are we doing? You would roll, let's call it in 100 rolls. So we're rolling it 100 times. How many 4s usually you would get? Well, let's see. Our probability of success is still 30%. Our n changed to 100. Our q is still 1 minus p, so it's still 0.7. So what are we getting? Well, the mean equals to n times p. So it's 100 times 0.3, which is 30. Our standard deviation goes to square root of npq. So in our case, that will be 100 times 0.3 times 0.7. So that would be equal to 21, square root of 21, right? 100 times 0.3 times 0.7, 21, and then square root of 21 comes out to be 4.58. So the usual range would be mean minus 2 sigma, mean in the middle, and mean plus 2 sigma. Mean minus 2 sigma is 30 minus 2 times 4.58. Mean was 30, and this is 30 plus 2 times 4.58. So this comes out to be 30 minus 2 times 4.58. That comes out to be 20.84. Mean still 30, and this comes out to be 39.16. So the usual range for this die for rolling a 4s in 100 right? The usual range for rolling a 4 in 100 rolls is between 20.84 rolls and 39.16. Now you cannot roll 20.84 4s in 100 rolls, but if I kept on repeating the sets of 100 rolls, all those sets will average eventually to that. Right? So if you roll 24s on a weighted die that gives you a probability of rolling a 4 30%, something is unusual about it. So let's say I roll the die 100 times, and I got what I get. I get 67 4s. Okay. So my question is this unusual? Well, let's see. If I use the z-score, which says x minus mu divided by sigma, this will give me the number of standard deviations my score is away from the mean. So that's 67 minus 30 divided by 4.58. Well, so that equals to 37 divided by 4.58. And I get 8.079. See, I have two decimal places here. I put 3 decimal places here. Anyways, I got this. What does this mean? Means I'm 8 standard deviations away from the mean, which means that I'm not usual. I'm not even very unusual. I'm very rare. Very, very rare. If you're wondering about how rare things are, is plus or minus 1 standard deviation was 68%. Plus minus 2 standard deviation within that range was 95. Plus or minus 3 standard deviations was 99.7%, which translates into 3 out of 1,000 are not, right? This is how much is outside. If you look at 6 standard deviations, and if you heard of 6 sigma, you will understand what I'm talking about. If not, don't worry about it. 6 standard deviations means 3.4 out of 1 million. And we have 8.079 standard deviations away. This thing is rarer than 3.4 out of a million. Which means this is so very highly unusual. I should have been playing lottery on that day. Right? Again, if it was within the first 2, that's usual. Anything beyond, so that's usual. This is unusual. Right? This is extremely rare. This is like, wow, that's rare. Is it possible? Yes, of course it's possible. But it's still extremely rare. And that ends chapter 3. I will be putting some practice problems online so you guys can get to practice it, but this is about it. Chapter 3 just introduces the probability and the binomial probability formula. Chapter 4, we're going to start talking about continuous random variable, and that's coming up next. Thank you, and again, reach out if you have any problems or comments. Otherwise, I'll see you guys next week, or I'm going to be talking to myself again. Who knows? Have a great day.